Okay, so doesn't look like there are very many spare handouts left at the front, but all the handouts are available on the web. And please don't forget to hand in your practice coursework. So this is the first examples class, and we're going to start by giving you a chance to write down the definition of what it means for a set to be bounded. And so I'm going to give you just a minute to, or maybe 2 minutes, to see if you can remember what it means for a set to be bounded. You're going to need that in order to be able to do part B, which is what it means for a set to be unbounded. So I'll just pause there and give you a couple of minutes to figure out the answer to 6 part A. Then I'll tell you the answer to 6 part A, and I'll give you a starter to help you going with 6 part B, and then you can have a go at 6 part B, and the helpers will come round as well to see how you get on with that. So I'll pause the recording there. So now you've had a little bit of time. There are in fact 2 different versions in the notes. So let's give you at least one version. So let S be a subset of d-dimensional space. Then S is bounded if, I'll put this in blue, if there exists some positive real number R such that S should be contained in the closed ball, radius capital R, centers on the origin. An alternative definition which you could use exists R greater than 0 such that for all x in S we have norm x less root R. That means the same thing. But what I want to point out here is that if you've missed out the there exists R greater than 0 bit, or if you just said without saying there exists R greater than 0, if you just said something like S is contained in, if you just did the second bit without the first bit, then what you've written is ambiguous and you won't be able to use it. Because if you don't say whether you mean there exists an R or for all R, if you miss out the quantifier, just say sort of R greater than 0, then I don't know whether you mean it's true for all of them or for at least one of them. So it's very important here that what you're saying is there is at least one value of R, implicitly big enough in this case. There's at least one big enough positive real number R so that the whole of that set S is contained in the closed ball with that radius. And if you miss out that first bit, then you won't have a workable definition. Now this second one is equivalent to the first one. All I've done is I've expanded out what this means, that to say that S is contained in this ball is just to say that for every point in the set, every point X in the set is also in this ball, but to say X is in the ball is to say that the norm of X is less than R. So that's just a way it was rephrased in the notes. And you could use either of these when you want to do 6 part B. So let me just get you started on 6 part B, which is what does it mean to be unbounded? That means you're not bounded. So for 6 part B, so you let S be a subset of R to the D again, then S is unbounded if and only if it's not true. Here's our symbol for not. Let me make that a bit smaller, because it's normally a bit smaller than that. It's if and only if it's not true that S is bounded. That's not very helpful because it has a not in it. And the idea in this part is to try and unknot it, so get rid of the knots as much as you can, and the more knots you get rid of, the better, the easier the statement gets to use. So I'll just move that a bit further to say that's the same as not there exists an R greater than 0 such that S is contained in the ball of that radius centered on the origin with a bar at the top. And now I leave it to you to use the standard negation system to sort that out. Now, you don't need to say such that. So that such that is optional. And by the time you negate it, it'll probably turn into something else. So let me give you a bit of time to see if you can negate that statement, see how much you can do in getting rid of anything that sounds like the word not. If you do a really thorough job of it, the word not won't be hidden in there at all. Okay, so I'll pause the recording there, and we'll come round and see how you're getting on. Okay, so with apologies for getting my not symbols the wrong way around before. Those are now correct, I hope. Then this is if and only if. Now, if it's not true that there exists a positive real number R of a certain property, that means that for all positive real numbers R, that property isn't true. So that's if and only if, for all R greater than 0, and I'll put an optional we have, so that's optional again. Just like the such that is optional, the we have is optional. You can use a comma if you want. We have that S is not a subset of the ball, closed ball, centered on the origin, radius R. Well, that's correct already, but it's implicitly got a not a subset of in, and it'd be nice to get rid of that not as well if you can. So this is, I'd say this is already okay. But I prefer to go even further. For all R greater than 0, I'll use a comma instead of a we have this time. There should exist an X in S such that X is not in the ball on the origin, closed ball on the origin, radius capital R. So to say that S is not a subset of the ball means there's at least one point in S which is not in that ball. But it's still got a not an element in. This is already correct, but if you want to get rid of that last bit of notness, you have to think about what does it mean. X is in that ball if and only if the norm of X is less than or equal to capital R. So if X is not in the ball, X is not in the ball if and only if the norm of X is strictly greater than capital R. That's the same as saying that X isn't in that closed ball. And that's my favourite version of the answer. So any of these last three lines are okay. You can work with any of those last three lines. Before that, it's very hard to work with. But any of these last three lines you can pretty much work with. But my favourite version is the last one. So the idea now is to use this definition of unbounded and the definition of bounded to help you in the next question. So what's the next question about? You have to try and sketch these three sets and try to decide whether or not they're bounded or unbounded, using carefully the definition from part 6. That means if you think it's bounded, you should come up with an explicit positive real number R that you think will do it, to show that the set is contained in that big ball centered on the origin. If you think it's unbounded, then you have to prove that there isn't a positive r that will do. And that means you've got to show that for every positive real number r, there's at least one point in the set that's further away from the origin than that. So that's a trickier proposition. It means that you're going to have to find a sort of formula in terms of r for the point you're going to exhibit that's further from the origin than r, but is still in the set. So here are your three sets, and I'm going to do the first one for you, though not necessarily to scale. Okay, so there's a point 2, 3, and a point 1, 6. Here are the points in your set. So A is a 2-point set, which means it's got 2 points in it, shown by the crosses. And now you're supposed to find a positive real number r big enough so that if you take a big ball centered on the origin, you'll get the whole of A into it. So I'll give you for free that there's only 2 points here, and if you take r to be the square root of 37 or bigger, and then if you do that, then A is contained in the closed ball centered on the origin radius r, so A is bounded. That's a really careful way of seeing that this set is bounded. You've actually figured out how big capital R has to be. Now, part 2, I'm going to let you try to sketch this yourself, and it should become apparent that in part 2 it's not a bounded set. That means that in part 2 you're going to have to try and find a formula for a point x which is in the set B but whose distance from the origin is greater than r. So for different r you're going to need different points x. So if you can, try to think of an explicit formula, a really easy formula, in terms of capital R for a point that's definitely in B, but further from the origin than distance capital R. And then for part 3, I'll leave that to you to sketch and think about. So we'll let you think about B and C now for the next few minutes. Sorry about that. That's the usual technological problems. B is the open right-hand half plane. So that was, it's xy in r squared such that x is greater than 0 which is the same as the product of these two unbounded intervals or it's the strictly positive real numbers crossed with R. Give you a sketch of it. It's a bit of a problem because you're trying to do an infinite sketch. And the first problem is you need to do a dotted line on the y-axis to show it's excluded. So about the best I could do is do some coloured dashes down the y-axis, and then I'll shade a bit to the side. I'll do a few dots because it goes on forever. This is so B is, it's a typical unbounded 2-cell. It's a shaded region shown. But we're supposed to prove it's unbounded. So let me suppose that you draw some disk around the origin, not a very good disk that, radius R, and you want to prove that you haven't got all the points of B in it. Then you need a formula for a point in B that is distance at least, well, bigger than R from the origin. So to prove B is unbounded, we need that for all R greater than 0, there exists an X in B with norm X bigger than R. So we'll let R greater than 0. And we're looking for a point X that's further from the origin than that. So here's our diagram of what we're going to do. And I already know we've got one example on the right, which we sorted out earlier. Anybody else? Who's got a formula for me for a point that's definitely in B, but which is definitely distance more than R from the origin? Can anyone name a pretty specific point in terms of R? You need to give me a couple of coordinates. Any suggestions? Yes? R plus 1 naught is a good one. So R plus 1 0 is in B, but norm of R plus 1 0 is equal to R plus 1, which is bigger than R, so R plus 1 0 is not in the ball on the origin radius R. You can take your X to be this point, and this shows the condition we need is holds, so B is unbounded. So have a look at this. You can, whichever big positive real number R you try, you just take this point, which I can just put on that sketch for you, which is out here. Here's the point R plus 1, 0. Shows that you haven't managed to swallow the whole of B into that ball. It doesn't matter which R you try, there's always at least one point outside. Of course, there's infinitely many points outside, but that's what's going on there. Okay, now that's how you prove very, very carefully that a set is unbounded, by actually giving a formula for a point in that set that's distance more than R from the origin. Now, the other set is a right-angled triangle with a boundary excluded. So this is, go back to what's the next part? That's part 3. It's those x, y, and r squared, so that naught is strictly less than x, strictly less than y, strictly less than 3. So that's a right-angled triangle, which everything lying within a bounded distance of the origin. I hope everybody's managed to sketch that one. If not, let me have a go at it for you. Naught less than x less than y less than 3. It will be not to scale as usual. So let me start by drawing y equals x, a bit of it. And here's your 3's. Here's x, here's y. It was naught less than x less than y less than 3. So x less than y means y is bigger than x. And I can also draw the lines y equals 3 and x equals 3. Let's see if I got this about right. Was it naught less than x less than y less than 3? So it looks like we're getting this region up here. So set C is the shaded region shown, all boundaries excluded. Excluding the boundary lines. So is that set bounded or unbounded? What do people think? Bounded, okay. What would be a good value for capital R? Any suggestions? What value of capital R will be big enough to make sure that you stay within that distance of the origin? You don't have to give me the best value. 4 would do. Would it? Let's have a look. How far are we over there? I think 4 might not be quite enough. Yep. 5 would just about do it. We're looking for 3 root 2 is the best you can do. And 3 root 2 is a bit bigger than 4. Here, here we can take r equals 3 root 2 or bigger, to show that C is bounded. Because C is contained in the closed ball centred on the origin, radius 3 root 2.